Let's move on now to measurements of the neuromuscular jitter. The phenomenon of jitter relates to the basic physiology of neuromuscular transmission, as demonstrated here in this slide, which is a recording of in-plate potentials in a patient with myasthenia gravis. In-plate potentials are measured by inserting very fine microelectrodes into muscle fibers near the in-plate zone. Action potentials are produced in the in-plate zone by the acetylcholine that is released from the nerve terminal. Normally, you would not see these in-plate potentials because in a normal neuromuscular junction, each of these in-plate potentials would be high enough to generate an action potential, which would mask the in-plate potentials, being much higher in amplitude. But because this is from a patient with abnormal neuromuscular transmission, we can see how the in-plate potential amplitude varies during successive activations of the nerve muscle synapse. The initial amplitude of a train of stimuli is high and then it falls, and you, I'm sure, are struck by the fact that this envelope and these waveforms look very much like the compound muscle action potential pattern seen in repetitive nerve stimulation. And that's not surprising because the basic phenomenon is the same. In-plate potentials vary in their amplitude. That variability is due to the quantal characteristics of neuromuscular transmission. The acetylcholine is released in discrete packages, each of which produces a definable depolarization of the in-plate, and the quantal summation produces stepwise changes in the in-plate potentials. This then translates into time changes in the action potential generation at the in-plate. This is a diagram of intracellular recordings made at an in-plate, again in a patient with myasthenia gravis. But this time the in-plate potentials are sufficient to generate action potentials during some stimuli. These are superimposed traces during repetitive stimulation. The low amplitude waves here are the in-plate potentials, which do not reach the threshold. The high amplitude spikes here are the action potentials that are propagated down the muscle fiber after the in-plate potential does in fact reach the threshold. The threshold is not constant, it varies up and down a little bit, plus the in-plate potentials are varying up and down a little bit, and that combined variability results in different times at which the action potentials are generated. And you see here that the action potentials do not superimpose, they vary because of this difference in time. This difference in time, this variability in the generation of the action potential, is the neuromuscular jitter we measure with the single fiber electrode technique. This is just a higher amplitude picture of the same phenomenon. This in-plate potential has a very sharp rise time and high amplitude, and it reaches the threshold early, and back in this portion of them they are slower, they're not as high, they don't reach the threshold as rapidly, and therefore they generate the action potential later. This can be seen most directly during single fiber EMG recordings made during axonal stimulation. This is a diagram of this technique. A monopolar needle electrode is inserted into the muscle near the in-plate zone in such a way as to get very close to individual motor nerve twigs. The motor nerve twigs are then stimulated with very small currents, and the recordings of the action potentials produced in the muscle fibers is made with a single fiber EMG electrode placed out distally in the muscle. And this is what you see in that circumstance. This is a normal stimulated jitter study. Here is the stimulus artifact, and we've begun measuring time when that signal is produced. And here are superimposed action potentials from a single muscle fiber during low frequency stimulation. And you'll see that these action potentials superimpose very tightly. There is very little jitter. Jitter here is 13 microseconds. Contrast this with a similar recording made from a patient with an abnormal neuromuscular transmission, and you'll see how this action potential out here varies in its timing. And if we calculate this variability, it comes out to 120 microseconds. During axonal stimulation measurements of jitter, we stimulate the nerve at a frequency that approximates the physiologic firing rate, somewhere between 5 and 10 per second. We exclude the first second of the recording in each train or after we make a rate change to remove the artifact that's produced by variability in firing rate. In some muscle nerve recordings, it's possible to stimulate not just the intramuscular nerve, but also the muscle fiber itself directly. If you're stimulating the muscle fiber directly, there's no jitter because there's no synapse. It's an electrical activation of the muscle. So the jitter that you would record in that circumstance would be very low. And if that's an issue, it's important to not measure jitter if it's less than 5 microseconds. This is a potential problem when you're making recordings from the EDC muscle in the forearm. But if you're doing jitter studies in a facial muscle and you're stimulating the facial nerve and recording out on the frontalis or the orbicularis, then there's no possibility of directly stimulating the muscle fiber. So that's not really a problem when you're doing facial nerve studies. You record signals from an adequate number of end plates to be sure that your sample covers the totality of variability within the muscle. And so we say you should try to measure action potentials from up to 30 end plates when you're doing axonal stimulation studies. There is a arithmetic relationship between the jitter that you measure during axonal stimulation and that which is measured during paired jitter measurements during voluntary activation, which is a technique that we'll come to next. So you could calculate the normal value of one technique from the normative data from the other technique. This is one of the major pitfalls of stimulated jitter studies when you're doing it with intramuscular stimulation. If you're using stimuli that are very close to the threshold and you stimulate a muscle fiber, that can induce jitter because the slight variability around this threshold that is inherent in the current flow and probably also in the activation threshold for the fiber can cause false jitter and even blocking. And it's very difficult to be sure that that's not happening. And if you're stimulating the muscle fiber directly and you get the low jitter, then that's another thing that has to be recognized. And as I mentioned, this is not a problem with facial nerve studies. These potential artifacts must be recognized while you're making the recording because they're very difficult to identify from pictures or even from tape recordings or other types of recordings.